Centrifugal pumps use a rotating device called an impeller to move fluid by stirring it faster and faster in a circular motion and then changing the increased speed into pressure. As the impeller stirs the fluid in a rapid circular motion, the centrifugal force is created that gives the pump its name. Compared with positive displacement pumps, centrifugal pumps have the advantage of being able to move higher volumes of fluids. However, they generally do not have the ability to exert as much pressure on the fluids as positive displacement pumps. Also, centrifugal pumps usually must be primed. The impeller is connected by a shaft and a coupling to a driver, such as an electric motor. During operation, the driver rotates the impeller, creating centrifugal force that pushes the fluid outward into the volute. A radial flow pump takes advantage of the maximum amount of centrifugal force that the impeller develops. Making maximum use of centrifugal force makes it possible for radial flow pumps to operate at higher discharge pressures than other types of centrifugal pumps, but they do not move as much fluid. In contrast, axial flow pumps are able to move large volumes of fluid, but only with a relatively low discharge pressure. The stuffing box is a section of the casing that encloses an assembly called the packing gland. The purpose of the packing gland is to regulate leakage past the shaft at the point where the shaft passes through the pump casing. Fluid could leak from the discharge side of the pump, through the space between the impeller and the casing, back into the suction eye of the impeller. Fluid leaking back into the suction eye would reduce the efficiency of the pump, because a certain amount of fluid would have to be pumped twice. Wearing rings fit snugly between the impeller and the casing, sealing off the space between them and minimizing leakage back to the suction eye. The timing of the symptoms is very important. If the symptoms occurred suddenly, then the problem is likely to be the complete failure of a part. If the symptoms developed gradually over a period of weeks or months, then the trouble probably involves the gradual wearing out of one or more parts. Often the symptoms of problems in a centrifugal pump can be seen. For instance, one indicator of a problem in a pump is an abnormal reading, usually a low reading, that can be seen on the discharge pressure gauge. Abnormal suction pressure can be seen on the suction pressure gauge. One thing though, if you see an abnormal reading, make sure that the gauge is functioning properly before assuming that the problem is in the pump rather than in the gauge. The pump should be shut down and prepared for disassembly. Whenever you're working on pumps or other machinery, you must make the equipment safe to work on. Following your plant's procedures for locking out and tagging out the equipment will ensure that the pump is not accidentally turned on while you're working on it. If you're not sure about your plant's lockout-tagout requirements, check with your supervisor. Pumps are one of the most common and most important types of machinery found in industrial facilities. Some pumps move raw material into processing systems, while others move products out of processing systems to storage or transportation. Still others move coolants or lubricants that can be vital to the proper and safe operation of a facility. Proper operation of these pumps is critical. Knowing how to properly troubleshoot, maintain, and repair pumps is one of the most important job skills you can have. In this part, we're going to take a look at pumps in general and compare the two most common types of pumps found in industrial facilities. No matter what kind of pump you're dealing with, its function is to move fluid from one place to another. By fluid, we mean any substance that can be pumped. This can be water, oil, refrigerant, chemicals, or even air. The two most common types of pumps found in industrial facilities are positive displacement pumps and centrifugal pumps. The difference between a positive displacement pump and a centrifugal pump is not what the pump does, but how it does it. A positive displacement pump uses a piston or other device to push or positively displace controlled amounts of fluid. In general, positive displacement pumps are not designed to move high volumes of fluids as compared with centrifugal pumps. However, they have the advantage of being able to exert greater amounts of pressure on the fluids they move, and they generally do not require priming. That is, they do not have to be full of fluid when they're started. Centrifugal pumps operate on a completely different principle. Centrifugal pumps use a rotating device called an impeller to move fluid by stirring it faster and faster in a circular motion and then changing the increased speed into pressure. As the impeller stirs the fluid in a rapid circular motion, the centrifugal force is created that gives the pump its name. Centrifugal force is the force that tends to push an object or material outward from the center of rotation. Centrifugal force is generated by any object or material moving in a circle. Compared with positive displacement pumps, centrifugal pumps have the advantage of being able to move higher volumes of fluids. However, they generally do not have the ability to exert as much pressure on the fluids as positive displacement pumps. Also, centrifugal pumps usually must be primed. In this part, we will examine the basic operation of a typical centrifugal pump. While the pumps you work on may look different or be more complex, we will use this simplified illustration to explain the basic principles of operation that are common to all centrifugal pumps. All centrifugal pumps have a casing, a suction inlet, and a discharge outlet. Inside the pump's casing is an impeller, which has a series of curved vanes that extend outward from the center. The pump's casing is designed so that the area around the impeller creates a gradually widening channel. This channel is called a volute. The impeller is connected by a shaft and a coupling to a driver, such as an electric motor. During operation, the driver rotates the impeller, creating centrifugal force that pushes the fluid outward into the volute. This outward movement creates a reduced pressure area at the point in the center of the impeller where the fluid is drawn in. This point is called the suction eye of the impeller. As a result of the reduced pressure, more fluid is drawn into the pump, so a constant flow of fluid is provided. As the impeller rotates, its outside edge moves through a greater distance than its inside edge. This means that as centrifugal force pushes the fluid outward from the suction eye, the fluid must move faster to keep up with the rotation of the impeller. As the fluid moves away from the impeller into the volute, the fluid contains a large amount of kinetic energy, or energy of motion. As the fluid expands in the volute, it slows down and loses kinetic energy. Because energy cannot simply disappear, the kinetic energy is converted into pressure, which forces the fluid out of the pump and through the discharge piping.
To minimize the chance of a fire or an explosion, oxygen should always be stored and used away from flammable materials. Oil, grease, and other petroleum products are highly combustible in the presence of oxygen. Even oil residue or a spark could trigger an explosion. Many different types of fuel gases can be combined with oxygen in oxy-fuel gas welding, but one of the most common is acetylene. We'll use acetylene for the examples in this program.
In this part, we'll look at some of the design characteristics that can be used to classify centrifugal pumps, and we'll see some of the advantages and applications of the different types. One way to classify centrifugal pumps is according to the direction of the fluid's path through the pump in relation to the shaft. The classifications are called radial flow, axial flow, and mixed flow. In a radial flow centrifugal pump, the impeller causes the fluid to make a 90-degree turn and move outward or radially from the suction eye to the tips of the impeller vanes. A radial flow pump takes advantage of the maximum amount of centrifugal force that the impeller develops. Making maximum use of centrifugal force makes it possible for radial flow pumps to operate at higher discharge pressures than other types of centrifugal pumps, but they do not move as much fluid. In contrast, axial flow pumps are able to move large volumes of fluid, but only with a relatively low discharge pressure. In an axial flow pump, The impeller moves the liquid through the pump along a straight path that is parallel to the pump shaft. Mixed flow pumps combine the characteristics of radial flow pumps and axial flow pumps. For this reason, mixed flow pumps can develop relatively high discharge pressures and still move large amounts of fluid. Another way that centrifugal pumps can be classified is by whether they have a volute or a diffuser. When the casing of a pump is designed so that the area around the impeller creates a gradually widening channel, the channel that is formed is called a volute. In some pumps, the volute is replaced by a structure that has a series of stationary vanes arranged around the impeller. This structure is called a diffuser. The vanes create a series of widening chambers that convert the kinetic energy into pressure in the same way that a volute does. The diffuser vanes direct the fluid outward in all directions as it leaves the impeller. The main advantage of the diffuser is that radial thrust is minimized. Centrifugal pumps can also be classified by the orientation of the shaft, either horizontal or vertical. Most centrifugal pumps are mounted horizontally. That is, the motor is beside the pump and the shaft's orientation is parallel to the ground. A major advantage of vertically mounted pumps is that they can be used in locations where the pump must be submerged in fluid without causing damage to the motor. In this example, a vertically mounted pump is submerged in a tank containing the fluid being pumped. The motor is mounted above the pump on top of the tank. Vertically mounted pumps can also be used where floor space is limited. Another way to classify centrifugal pumps is by whether the pump is a single-stage pump or a multi-stage pump. Each stage consists of an impeller and a volute. Multi-stage pumps generally produce higher discharge pressures than is normally possible with a single-stage pump of similar size. Centrifugal pumps can also be classified according to the type of impeller they use. Impellers can be closed, open, or semi-open. A closed impeller has vanes that are enclosed by metal coverings called shrouds. The shrouds direct the flow of fluid between the vanes. Closed impellers are often used with low viscosity or thin fluids. Closed impellers can be classified as single suction or double suction. This impeller is a single suction impeller. It has a suction eye on only one side. This impeller has suction eyes on both sides, so it is a double suction impeller. The advantage of a double suction impeller is that it helps minimize axial thrust. Open impellers are used to pump thick fluids or slurries. A slurry is a thick, viscous fluid, usually containing small particles of solid material that could clog a closed impeller. An open impeller has no shrouds to direct the flow of the fluid. While this design helps prevent clogging, it's less efficient than a closed impeller for moving fluids. Semi-open impellers have one shroud to direct the fluid between the vanes. Semi-open impellers can be used for pumping either thin fluids or heavier fluids and slurries. In this part, we looked at some design variations that can be used to classify centrifugal pumps. It's important to remember that one pump can be classified by one or more design variations. For example, this pump is a multi-stage radial flow pump. Its impellers are closed impellers. The impeller in the center is a double suction impeller, and the others are single suction impellers. Any or all of these design characteristics might be used to describe this pump. Now try a question about centrifugal pump classification. In this topic, we saw the two most common types of pumps that are used in industry: positive displacement pumps and centrifugal pumps. We looked at the basic operation of centrifugal pumps, and we examined some of the ways that centrifugal pumps can be classified. Now try some practice questions on this material. The casing consists of two halves, which are held in place by casing bolts. The seam between the halves is sealed by a gasket, which prevents fluid from leaking out between the two halves of the casing. The casing of a centrifugal pump serves several purposes. We can see how these purposes are accomplished by looking at how the inside of the casing is shaped. One purpose of the casing is to contain the fluid being pumped and direct the fluid as it moves from the impeller to the volute and out through the discharge piping. The casing also houses the internal parts, holds them in their proper places, and protects them from dirt and damage. In addition, the casing forms the volute and provides connection points for the pump's suction and discharge piping and other necessary fixtures. The volute is part of the casing structure. It's the area around the impeller that creates a gradually widening channel, which is connected to the discharge piping. The stuffing box is a section of the casing that encloses an assembly called the packing gland. The purpose of the packing gland is to regulate leakage past the shaft at the point where the shaft passes through the pump casing. The packing gland is described in detail in the section of this program called Internal Parts. On this pump, the shaft passes completely through the casing, so there are two stuffing boxes, one on each side of the pump. The slop drain provides a path for the regulated leakage from the stuffing box to be directed away from the pump and into the drainage system. The slop drain in this example is in the bottom of an extension on the casing that forms an open well to catch the leaking fluid. The gland sealing line provides a means to deliver water to the stuffing box. If the pump is moving water, the water can be delivered from a point on the upper casing where water is discharged from the impeller. In some applications, the water is delivered from an external source. The water serves as lubricating fluid for the stuffing box to minimize friction between the packing material in the stuffing box and the shaft as the shaft rotates. This water from the gland sealing line ultimately leaks out of the stuffing box along with the controlled leakage from between the shaft and the casing. The impeller is the rotating part of a centrifugal pump that moves the fluid being pumped and creates the centrifugal force that gives the pump its name. In this example, the impeller is located here, in the center of the pump. Let's take a closer look. This is a closed impeller, which is the most common type of impeller. Here, along the edge, you can see the tips of the vanes that move the fluid as the impeller rotates. The metal plates that cover the vanes are called shrouds. The shrouds direct the flow of the pumped fluid and give structural support to the impeller's vanes. If we were to remove one of the shrouds, we would see vanes that look like the vanes on this semi-open impeller. The suction eye is at the center, where the impeller is attached to the shaft. This is the area where the pumped fluid enters the impeller and begins to spiral outward to the volute. This impeller has two suction eyes, so it is a double suction impeller. The impeller is the key element that moves the fluid that is being pumped. The other parts function to keep the impeller spinning smoothly. Wearing rings are replaceable rings on the casing or the impeller that wear as the pump operates. In some facilities, they're called wear rings. As the impeller rotates within the pump casing, it should not touch the surface of the casing at any point. If it does, friction between the impeller and the casing will wear the impeller down at the contact point. To avoid this, there is space between the impeller and the casing, but this presents a problem too. Fluid could leak from the discharge side of the pump, through the space between the impeller and the casing, back into the suction eye of the impeller. Fluid leaking back into the suction eye would reduce the efficiency of the pump because a certain amount of fluid would have to be pumped twice. Wearing rings fit snugly between the impeller and the casing, sealing off the space between them and minimizing leakage back to the suction eye. The wearing ring in this example is held by the casing and is stationary, with the impeller rotating inside of the ring. This ring is called a casing wearing ring. The clearance between the impeller and the wearing ring is quite tight, but the impeller should not be in contact with the wearing ring as it rotates. Wearing rings are designed to wear, and they are less expensive to replace than the impeller. The packing gland assembly consists of several components. The packing gland fits into a space in the pump's casing called the stuffing box. The purpose of the packing gland is to provide a seal to control leakage at the point where the shaft passes through the casing. In this pump, the seal is provided by rope-style packing material. Another way to seal the point where the shaft passes through the casing is to use a mechanical seal. Mechanical seals are often used in pumps that move chemicals that would be hazardous if they were allowed to leak through the stuffing box. The components that make up the packing gland on this pump are a throat bushing, rings of packing material, and a lantern ring. The throat bushing is the component of the packing gland that is closest to the impeller. It prevents the packing material from being forced into the suction eye of the impeller by the gland follower, which is the component that compresses the packing material. The packing material provides the seal that controls the leakage between the shaft and the pump casing. This packing material is in the form of rings. The packing rings are made of a soft, pliable material, and they resemble short lengths of rope. When they are properly fitted into the packing gland, the rings fill the space between the shaft and the casing. Because the packing material is soft, the shaft can rub against it without being damaged. But no matter how soft the packing material is, it must be kept lubricated in order to minimize friction and the resulting heat. Without proper lubrication, the friction caused by the rotation of the shaft can generate enough heat to scorch the packing, and scorched packing could cut grooves in the shaft. Usually, packing is coated with a lubricant such as graphite or Teflon, but additional lubrication is required to protect the packing material and the shaft. In a pump like this one, which pumps water, additional lubrication can be provided by the controlled leakage of water from the area between the shaft and the casing into the packing gland. If more water is needed for lubrication, it can be taken from the discharge end of the pump and fed into the stuffing box through a gland sealing line. In this example, there are 2 sets of packing rings in the packing gland. The lantern ring distributes water from the gland sealing line into the packing gland. In the packing gland of this example pump, there is a lantern ring between 2 sets of packing rings. When the water from the gland sealing line enters the stuffing box, it's forced into the channel in the lantern ring. There are holes in either side of the channel. These holes allow water to escape from the channel and flow into the packing material. Centrifugal pumps that do not use a gland sealing line do not need lantern rings. The gland follower is used to hold the packing gland assembly in place and compress the packing material in the stuffing box. Tightening or loosening the nuts on these bolts adjust the gland follower to exert the right amount of pressure on the packing. The right amount of pressure is important because the pressure controls the amount of fluid that flows through the packing gland. The fluid is used to lubricate the packing material. If the nuts are too tight, not enough fluid will flow through the gland, and the packing material might not be adequately lubricated. If the nuts are too loose, there could be excessive leakage around the pump shaft. The flinger is a collar that is attached to the pump shaft between the stuffing box and the housing for the shaft bearings. The flinger is referred to as a slinger in some plants. It's designed to prevent the controlled leakage between the shaft and the pump casing from getting into the bearings that support the shaft. The shaft bearings hold the shaft in its proper position and allow it to rotate freely. The bearings are supported and protected by the bearing housings at each end of the pump. On this end of the shaft, there is a thrust bearing and a radial bearing. The thrust bearing keeps the shaft from moving back and forth in the direction parallel to the shaft. The radial bearing keeps the shaft from moving up and down or side to side, that is, in a direction perpendicular to the shaft. Another radial bearing is located in the housing at the other end of the pump. The shaft of a centrifugal pump is a carefully machined cylindrical metal bar that transfers the rotational energy from a driver, usually an electric motor, to the pump's impeller. The pump shaft must be properly aligned with the driver's shaft to achieve smooth rotation and the best possible transfer of the driver's energy. The pump's other internal parts are attached to the shaft. Problems with the shaft can be difficult and expensive to fix. So some pump shafts are equipped with shaft sleeves, which can protect the shaft from various kinds of damage. The sleeves fit over the shaft so that if any damage occurs, it occurs to the sleeve and not to the shaft itself. In this topic, we've looked at the main external and internal parts of a typical centrifugal pump. Although most centrifugal pumps have the same basic parts, the size and arrangement of the parts will vary from pump to pump. Now take some time to try some practice questions on this material. In this part, we'll look at some general procedures that can apply to troubleshooting any centrifugal pump. Troubleshooting is the process of identifying and fixing problems. Troubleshooting a centrifugal pump usually begins with a report from the pump operator that there is something wrong with the pump. One of the first steps in troubleshooting a pump is to talk to the pump operator. The operator is responsible for the pump's operation and is probably the person most familiar with the pump's operating characteristics. Important questions you should ask include: what are the symptoms? When did the symptoms first appear? Did the symptoms occur suddenly, or did they develop over a period of time? The timing of the symptoms is very important. If the symptoms occurred suddenly, then the problem is likely to be the complete failure of a part. If the symptoms developed gradually over a period of weeks or months, then the trouble probably involves the gradual wearing out of one or more parts. Other questions to ask are: what steps, if any, has the operator taken to attempt to solve the problem? And did any changes in the pump's operating characteristics occur, such as changes in suction or discharge pressure? Changes in a pump's operating characteristics can also indicate a possible problem in the system that the pump is a part of. For example, a drop in suction pressure might indicate a blockage in the suction piping, or abnormally high discharge pressure could indicate a blockage in the discharge piping. Either of these problems could be caused by such things as clogged strainers, incorrect settings of suction or discharge valves, or even faulty gauges. It's important to be sure that other system components are working properly before you focus on the pump. Remember, anything the operator can tell you about the condition of the pump and the other system components is to your advantage. Unless the problem is so severe that the pump cannot operate at all, you usually will first inspect the pump while it is running. Before you begin to inspect the pump, there are several things you need to get together, such as tools, test instruments, manufacturer's manuals, and any other information about the pump that may help you in your troubleshooting effort. The specific items you will need will depend on the specific pump and on your plant's procedures. Also, certain precautions must be taken whenever you're working close to an operating pump. Wear all of the personal protective equipment that is required by your plant's safety procedures. This may include a hard hat, eye protection, and, if necessary, hearing protection. Don't wear loose clothing when you're working around rotating equipment. In this part, we'll examine some of the symptoms of problems that can be detected in an operating centrifugal pump, and we'll see what might be causing those symptoms. There are three types of symptoms that can be detected in an operating pump: symptoms you can hear, symptoms you can see, and symptoms you can feel. We'll start with symptoms you can hear. There are several abnormal sounds that you might hear from a centrifugal pump. One is a loud rattling or clanging noise. This could be the result of a broken part or other object loose inside the casing. Another is a growling or howling sound. This usually indicates worn or damaged bearings. A high-pitched screeching is commonly produced by metal-to-metal contact between rotating and stationary parts. If you hear any of these sounds, you can pinpoint the source of the sound by using a stethoscope, a brass sounding rod, or even a short length of pipe. These devices amplify the sound coming from the point of contact with the pump. By listening at different points on the outside surface of the pump, you can determine where the sound is coming from. Another abnormal sound that you may hear coming from a centrifugal pump is a loud rattling that sounds like marbles rolling around inside the pump. This is an unmistakable sign of cavitation. Cavitation is the formation and subsequent collapse of bubbles inside the pump's casing during operation. Cavitation occurs when the fluid being pumped reaches the boiling point, which can happen if the pressure of the fluid becomes too low at the suction eye relative to the temperature of the fluid. When boiling occurs, some of the fluid turns to vapor, which creates bubbles in the fluid. The bubbles caused by cavitation move with the fluid from the suction eye out toward the edge of the impeller, where there is increased pressure. They collapse with great force, resulting in a shock wave that can damage the metal surface of the impeller and the casing. In pumps moving cold fluid or moderately warm fluid, changes in pressure generally will not be enough to cause the fluid to boil. However, if the fluid being moved is near its boiling temperature, it's possible that it will begin to boil in the low pressure of the suction eye. To prevent cavitation, the amount of suction head or pressure at the suction eye must be maintained above the pressure at which the fluid will boil. This pressure is usually a minimum predetermined value for the pump, which is specified by the manufacturer. The technical term for this value is the pump's minimum net positive suction head, or NPSH. As long as the pump moves fluids in the proper temperature-pressure range, there should be no problem. Cavitation can occur, however, if the suction valve is not open all the way, or if the suction port is somehow blocked, resulting in a further reduction of pressure at the suction eye. When the sound of cavitation is severe, the pump should be shut down. The constant force of the collapsing bubbles can eventually disintegrate the metal of the vanes and the inside surface of the casing. Other signs of cavitation include rapid fluctuations in suction pressure and overheating of the pump casing. Often the symptoms of problems in a centrifugal pump can be seen. For instance, one indicator of a problem in a pump is an abnormal reading, usually a low reading, that can be seen on the discharge pressure gauge. Abnormal suction pressure can be seen on the suction pressure gauge. One thing though, if you see an abnormal reading, make sure that the gauge is functioning properly before assuming that the problem is in the pump rather than in the gauge. On some pumps, you may be able to see abnormal readings on instruments that indicate current draw by the motor, or bearing and lubrication temperature or pressure in a forced lubrication system. Another visible symptom on an operating pump is too much or too little leakage from the stuffing box. This leakage is referred to as leak-off. Too much leak-off can mean that the gland follower needs tightening. If that doesn't solve the problem, then the packing is probably worn and must be replaced. Too little leak-off indicates that the gland follower is too tight, or that the gland sealing line or the lantern ring is blocked and must be cleaned out. Leakage from around the casing flange indicates that the casing bolts may need to be tightened, or that the flange gasket may need to be replaced. Lubricant leaking from a bearing housing could be caused by a cracked housing or a faulty seal. This loss of lubrication can cause damage to the bearings. Excessive vibration and high temperature are two symptoms that can be felt. Vibration can sometimes be detected by placing a hand on the pump's casing. Be careful when you place your hand on a pump. The pump could be very hot or very cold. You should use a vibration meter to check for excessive vibration whenever possible. Excessive vibration may be a sign of shaft and coupling misalignment, a bent shaft, or some other shaft problem. Other possible causes of excessive vibration include such things as damaged bearings or wearing rings. The sound that accompanies vibration can indicate what the problem is. For example, vibration along with a howling or growling sound could indicate damaged bearings. Overheating is another symptom that can be felt. Typical points for overheating are the bearings and the stuffing box. Excessive heat in either of these locations usually indicates a problem with lubrication. It's good practice to use a temperature measuring instrument, such as a pyrometer, to check for overheating. It's possible to check for overheating by placing a hand on the stuffing box or the bearing housing, but do this with great caution. You could get a nasty burn. How hot is too hot? This will vary, so you'll need to refer to the manufacturer's manual and other information about the specific pump you're working on. Overheating of any part of a pump often indicates a serious problem. If the problem cannot be corrected while the pump is running, the pump must be shut down to avoid serious damage. Although we've categorized the symptoms of centrifugal pump problems according to how you detect them, it's important to realize that more than one symptom will often appear at the same time. In this part, we've looked at various symptoms that can be detected in an operating pump, and we've identified some of the causes of those symptoms. Now try a question to check your understanding of the material in this part. In this part, we'll look at some of the internal parts of a centrifugal pump that you may need to inspect when you're troubleshooting a problem. Unless a pump problem can be solved by adjustments to external parts of the pump, such as the gland follower or the casing bolts, or the system that the pump is part of, you'll need to open the pump and inspect the internal parts to get to the cause of the problem. The pump should be shut down and prepared for disassembly. Whenever you're working on pumps or other machinery, you must make the equipment safe to work on. Following your plant's procedures for locking out and tagging out the equipment will ensure that the pump is not accidentally turned on while you're working on it. If you're not sure about your plant's lockout-tagout requirements, check with your supervisor. For this example, the pump has been moved to the shop for disassembly and inspection. Once you've opened the pump's casing and gained access to the internal parts of the pump, there are several things to look for that could be the cause of trouble. For example, worn or damaged wearing rings will result in discharge fluid leaking back to the impeller's suction eye. As a result, discharge pressure drops and the efficiency of the pump is lowered. Worn or damaged wearing rings must be replaced to restore the pump's efficiency. A clogged lantern ring or gland sealing line prevents essential lubrication from flowing through the packing gland. These situations require a thorough cleaning of the clogged parts. Worn or damaged packing is one of the most common pump problems. If the packing is damaged, it will not provide adequate sealing of the stuffing box, resulting in excessive leak-off out of the packing gland. Packing that is worn, damaged, or inadequately lubricated can also damage the shaft. Packing that is worn or damaged must be replaced. Damage to the shaft can include ridges or grooves cut into it by inadequately lubricated packing material that has become scorched by excessive heat from friction. Before a new or repaired shaft is installed, it's important to make sure that the cause of the damage has been eliminated. Otherwise, the replacement shaft will be damaged as well. Bearing problems can sometimes be detected by rotating the shaft by hand. If there is excessive drag, it could be caused by bad bearings. More often, however, wear or damage to the bearings can only be detected by removing the bearings from their housings and inspecting them. Bearing problems are most often caused by inadequate lubrication. Damaged bearings must be replaced. Besides replacing the bearing, you must eliminate the cause of the loss of lubrication so that the same problem will not happen again. The impeller is the key component of a centrifugal pump because it moves the fluid in the pump. Damage or other problems with the impeller will result in a loss of pump efficiency. The impeller might get clogged by solid materials in the pumped fluid. The impeller might have been mounted incorrectly during an overhaul. Or it could have worked its way loose from the shaft, in which case it would not rotate at all. Another possible problem with impellers is damage from cavitation. Damage caused by cavitation most often appears along the edge of the impeller. The most common problem with impellers is wear that occurs at the point of contact with the wearing rings. This wear can allow discharge fluid to flow back into the suction eye, reducing the pump's efficiency. If the pump was making loud rattling noises while it was running, the casing should be inspected for broken parts or other debris. Foreign objects or fragments of broken parts in the pump should be removed as soon as possible. If they're left inside the pump, they will cause more damage. In this topic, we've examined some general considerations associated with troubleshooting a centrifugal pump. We've looked at some common symptoms that can be observed in an operating pump. And we've looked inside the pump for problems that can only be detected by careful inspection of the pump's internal parts. While the pumps and the parts we've looked at are typical of many found in industrial facilities, centrifugal pumps vary in size and shape and in the specific arrangement of the parts. Always refer to the manufacturer's manuals for specific information when you're working on a pump. Now take some time to try some practice questions on what we've covered in this topic.